Let's discuss first Dirichlet's theorem that says that for every absolutely convergent series of complex numbers, sum of an, every rearrangement that we make of this series will converge, and all those rearrangements will converge to the same number. Okay. So in that sense, an absolutely convergent series behaves very similarly to what we are used to see with finite sums. Okay, here something we need to discuss first is what does it mean, a rearrangement of the series? But let's give a precise definition. Okay, here what we have is a rearrangement of the natural numbers. Okay, it's just a permutation of those, of the sequence of natural numbers. Actually, we don't need the zero, so let me take it out. What we have here, the Kn, is a permutation of the original list where its number appears only once. Okay. All right. So once that is clarified, these are going to be the indices. So we have our series, sum of AK. And here what we are going to do to rearrange, we are going to pass to a series that is the sum of the AKN from n equal 1 to infinity, following the sequence Kn that is a permutation of the original list. Okay, and just to keep it simple, we are going to call this AKN with a prime. Okay, so we will say AK prime. Or we can call it AN actually. That is more proper. Okay, so then we say that this is a rearrangement of the original series. Okay. Now, we need this definition just so that we can write easily in the proofs of the theorems, okay? So now, let's prove the theorem. So in this case, let's pick a rearrangement, or better, you give me a rearrangement, the sum of an prime okay, and let's say it has partial sums is n prime. Okay. So now, given epsilon, we claim, let me write that in a new line. We claim that there exists some integer, capital N, such that for every m bigger or equal than n bigger or equal than capital N, then the sum from n to m of ai is less or equal than epsilon. Okay, this is actually not a claim, this is just Cauchy convergence, because we know that the series is absolutely convergent, the series with absolute values converge, and because it converges in the sense of Cauchy. Now, what we are going to do is to choose some number p, okay, such that all the integers, 1, 2, and so on, all the way up to n, capital N, are contained in the set K1, K2, and so on, all the way to Kp. Remember, because they are shuffled, it's a permutation. So these numbers, 1, 2, all the way through capital N, will be randomly assigned, okay, in a long sequence. But because it's a finite number of them, if we wait long enough, okay, there will be some position P such that by Kp, all the numbers 1, 2, all the way through capital N have already appeared in the sequence K1 through Kp. Okay, so that's what we do. And now with this gives us a rearrangement. Okay, and now we know for sure that for n bigger than p, lowercase n, then the numbers a1 through an will have appeared in Sn prime, okay? And when we look at Sn minus Sn prime, how to write this? Does not have a1 through an, okay? Because a1 through an appear in both Sn and Sn prime, so they cancel out. So what we get is that Sn minus Sn prime will be as small, as large, at most, as epsilon. Okay, because we saw before here, okay, we saw that was the largest we could get for any m and n bigger or equal than capital N. So once we know this, then it's clear that Sn prime as a sequence converges to the same limit, the same sum as Sn. And we are done.